In reinforcement learning, we often talk about efficiency, but what does that really mean? Usually, we focus on statistical efficiency. How many samples does an algorithm need to converge to a near-optimal policy? But there's another critical dimension, computational complexity. How much time and memory does it take to compute that policy? This is especially important when we bring in function approximation, a technique that allows us to handle massive state spaces by representing value functions with compact, low-dimensional features. Linear function approximation is one of the most widely studied and theoretically tractable forms. But here's the twist. Even when we assume that value functions are exactly linear in some feature representation, we can still run into intractable computational barriers. Today, we dive into a new and powerful result from Cheyenne Karami and Zaya-Oki Tan at the University of Alberta. They explore a setting they call partial qπ-realizability, a middle ground between two well-known assumptions in RL theory. Let's unpack this. The spectrum of realizability. At one end of the spectrum is q*realizability. We assume only that the optimal action value function q is linear in some feature vector. This is a very weak assumption. It says nothing about non-optimal policies. It's flexible but also risky. You might learn a good policy, but you can't guarantee the value estimates are accurate elsewhere. At the other extreme is qπ-realizability. We assume that every policy's value function, not just the optimal one, is linear in the same feature space. This is a very strong assumption. But here's the good news. Under this setting, and with access to a generative model, the ability to query any state-action pair, we can design efficient algorithms that find near-optimal policies in polynomial time. So where do we stand in between? That's where partial qπ-realizability comes in. This framework assumes that there's a specific class of policies, say, deterministic greedy policies or stochastic softmax policies, such that for every policy pi in pi, the action value function qπ is exactly linear in a given feature map phi. Importantly, this is weaker than full qπ-realizability. We don't require linearity across all policies. But it's stronger than q*realizability. We're not just approximating q. We're assuming exact linearity for a whole family of policies. This makes the assumption more realistic. In practice, we often care about learning within a structured policy class, like those generated by a neural network with fixed architecture, or policies derived from a parameterized family. But here's the punchline. Even under this seemingly reasonable assumption, learning a near-optimal policy remains computationally intractable. Karami and Tan prove two striking results. First, consider the case where pi is the set of deterministic greedy policies, policies that act greedily with respect to some weight vector theta. They define a complexity problem called linear RL, where the goal is to find an epsilon optimal policy under partial qπ-realizability. They show Theorem 3.1. Solving linear RL for epsilon less or equal to 0.05 is NP-hard. This means, unless p equals NP, no polynomial time algorithm can solve this problem. Even though we're only learning within a class of linearly realizable policies, and even though we have a generative model, the problem is still intractable. Why? Because the structure of the policy class, greedy policies parameterized by theta, can encode hard combinatorial problems like max3 SAT. Their proof hinges on a reduction, from delta max3 SAT, a known NP-hard problem, to linear RL. They construct an MDP where each state corresponds to a partial assignment of variables. Actions correspond to setting a variable to true or false. The reward at the end is the fraction of clauses satisfied. The feature vectors are designed so that greedy policies correspond to specific truth assignments. The value function under any greedy policy is linear, satisfying the partial qπ-realizability condition. So if you could efficiently find a near-optimal policy in this MDP, you could solve the original max3 SAT instance. Since max3 SAT is NP-hard, so is this RL problem. Now, what if we go beyond deterministic policies? Enter softmax policies, stochastic policies that select actions probabilistically based on their expected rewards. These are central to modern RL methods like policy gradients and actor-critic algorithms. Now the challenge is different. Deterministic algorithms can be ruled out by NP hardness, but randomized algorithms, which are standard in RL, are harder to rule out. So Karami and Tan turn to a stronger hypothesis, the randomized exponential time hypothesis, or rETH. rETH, there exists a constant c, such that no randomized algorithm can solve 3 SAT in 2c, n, time with error probability less than 1/3. Under rETH they prove Theorem 3.2. Under rETH, no randomized algorithm can solve linear RL in time exp, polylog d1/3, with error probability 1/10 for small enough epsilon. This is a stronger result than NP hardness. It rules out any efficient randomized algorithm, even those that use randomness to explore. And here's the kicker. The policy class pi-SM includes all greedy policies. So even though we're now working with a richer, stochastic policy class, the hardness persists. In fact, the result mirrors the known hardness in the q*realizability setting, suggesting that computational difficulty is fundamentally tied to the structure of the function approximation, not just the policy class. These results are not just theoretical curiosities. They reveal a deep truth. Even when you assume exact linear realizability for a natural class of policies, And even when you have full access to a simulator, learning a near-optimal policy can still be exponentially hard. This has serious implications for real-world RL systems. Deep RL models often use linear or near-linear function approximators in their value heads. Policy classes are often parameterized by weights, like in neural nets, which can generate greedy or softmax-like behavior. Yet despite this, we can't guarantee efficient learning, even in theory. So why do these algorithms work in practice? Because they're not solving the worst-case problem. They succeed under additional structure, smoothness, low-rank features, or low-variance dynamics that isn't captured by the worst-case analysis. But this also means, if you want a provably efficient algorithm, you need stronger assumptions. The paper by Karami and Tan isn't just a negative result, it's a boundary marker. It shows that partial qπ-realizability bridges the gap between q** and qπ, but doesn't eliminate hardness. The computational barrier isn't just about approximation error or lack of access to the optimal policy. Even when you know the value function is linear for a whole policy family, learning that policy can still be intractable. This reinforces a crucial insight. Statistical efficiency and computational efficiency are not the same. You can have a sample-efficient algorithm under q** realizability, but if the computation required to find that policy is exponential, you're no better off. And now, even under partial qπ-realizability, a setting that seems more favorable, that barrier remains. If you're designing a reinforcement learning system with function approximation, don't assume that linearity implies tractability. Don't assume that a generative model makes everything easy. And don't assume that expanding your policy class helps. Sometimes, it just makes the problem harder. The real challenge isn't just learning the value function, it's computing the policy that maximizes it. And sometimes, that computation is fundamentally hard. So next time you hear about a new RL algorithm with linear function approximation, ask, is it computationally efficient in the worst case? Because as this work shows in the world of partial qπ-realizability, the answer may be a resounding and unavoidable no. This research was presented at NeurIPS 2025. For the full paper, check the rETH 2510, 21888 v1.